Every structure begins with precise measurement.
And every measure starts with trigonometry.
In this presentation, we will show you how trigonometry became our blueprints.
Hola, Nayushans! We are students from College of Education, major in Mathematics, and today we present our project entitled Designing the Future Proposed Architectural Model of the Measured Building.
Trigonometry comes from the Greek words trigonon, meaning triangle, and metron, meaning measure. Deals with the relationships among angles and sides of triangles. In real life, trigonometry is used by architects, engineers, and surveyors to determine heights and distances that are difficult to measure directly. Good day, Naystians! To start our report, let's now take a closer look at how we gathered our data using the principles of trigonometry. To determine the height of the graduate school building here at the NEUST Sumacab campus, we relied on simple yet reliable instruments, a protractor to measure the angle of elevation, and a measuring tape to record our distance from the structure. We conducted two separate observations at different points to ensure accuracy and consistency. Our first observation point, positioned 35 feet away from the building, we measured an angle of elevation of 50 degrees. For the second data point, we moved farther standing 51 feet away, where the angle of elevation increased to 60 degrees. Our observer's eye level was recorded at 4.83 feet, which we considered in our final height calculation. To compute the height, we used the tangent function. Tan theta equals height over distance, a fundamental tool in solving indirect measurements. With this data gathered and verified, we were ready to move on to the computation phase. The next reporter will explain the computation and trigonometric application.
Using the tangent formula, we computed the height from both distances. For our first calculation, we measured the distance from the reference point to the base of the object as 35 feet, with an angle of elevation of 50 degrees. Using the tangent function, we computed the height to be 34.2 feet. For our second calculation, we increased the distance to 51 feet and measured a new angle of elevation of 60 degrees. Applying the same tangent formula, the height we obtained was 34.27 feet. When we compare the two results, the difference is only 0.7 feet. This very small discrepancy shows that our measurements are consistent and that trigonometry provides accurate and reliable results when applied correctly.
After computing the actual height of our building using trigonometry, we move on to creating our scale architectural drawing and 2D model. To make the building fit on paper and still keep it accurate, we use a scale of 1 inch equals 5 feet. This means every inch in our drawing represents 5 feet in the real structure. We adjust this scale when necessary to make sure the interior design remain clear and easy to interpret. Using the scale, we convert the real measurement into their scale version. This allowed us to produce a design that accurately reflects the height we calculate earlier. While building the drawing and the model, we made use all dimension, proportion, and angle were measured carefully. This ensures the scale design stay true to the actual building, just in a smaller, more manageable size. Overall, this step show how our mathematical calculate were applied in a real design, helping us create an accurate and visually realistic presentation of the building. The next reporter will present the design improvements of the building.
For the enhancement phase of our design, we focus on improving the building's functionality, sustainability, and accessibility. Here are the design improvements we propose. First, zonal panel to reduce electricity consumption and support sustainability. Second, glass windows to maximize natural lighting and reduce dependence on artificial lighting. Third, accessibility ramps to ensure inclusivity and provide easier access for persons with disabilities. Fourth, vertical garden to improve ventilation, reduce heat absorption, and enhance the building's aesthetic appeal. And lastly, designated parking area to provide organized parking for vehicles and reduce traffic congestion around the building, making the campus more efficient and convenient for students and faculty. These improvements combine function, innovation, and visual appeal. Our goal is to design not just a building, but a future-ready, sustainable, and inclusive learning space.
In conclusion, these performance tasks help us apply trigonometry in a real-world situation. We prove that the height of a structure can be measured accurately using only basic tools and trigonometric functions. At the same time, these activities strengthen our skills in design, computation, collaboration, and problem solving. Trigonometry is not just numbers. It is a tool that builds the future.
Our presentation ends here, but the possibilities of trigonometry in real-world design continue beyond the classroom.